So let's look at this particular solution then. There it is at the top, y equals minus 3x, 3 cos 2x plus 8 sin 2x. That is our particular solution. If we plotted it, we will get the function that we're interested in. However, we're going to use this compound angle formula that we've come across before to help us to rewrite this particular solution in this form. And this is a useful form to write it in, because if we compare this with stuff we've talked about before, this wave function, this sine function, this is the amplitude of the wave function, and this is a phase. So if we can write it in this form, we'll get something that's a bit more familiar to it. It'll give us a wave with a particular amplitude and phase angle. So that's why we're going to do it. This compound angle formula may be familiar to you. We've talked about it before, and it can be proved quite straightforwardly using trigonometric ideas from Pythagoras of right angled triangles. And there is a proof available if you're interested. But we end up with this. And there are others, if you remember. There's 4 of them. For sine A plus B, sine A minus B, cos A plus B, and cos A minus B. Now, if we look at this and compare it with this, the sine x plus alpha, where alpha is the phase angle, we're going to sort of work in reverse. And we're going to think about this r sine x plus alpha, and in our particular solution, look, we've got 2x. So I'm going to replace this with a 2x, this here, because that's what we're using in our particular solution. So in other words, we can say r sine 2x plus alpha can be written as, let me just move this to one side. It can be written as r, and now think of this sine 2x plus alpha, and think of this. So A is going to be our 2x, and B is going to be our alpha, and we're going to rewrite sine 2x plus alpha using this. So we can write sine 2x cos alpha plus cos 2x sine alpha. If we look at our particular solution at the top and compare it with this, so there's our particular solution, and here is our expression underneath here. We've got a cos 2x. We've got a cos 2x term. So the sine of the alpha is actually 3, and the cosine of alpha is actually 8. And the sine of alpha and the cosine of alpha, these are constants in front of the sine and the cosine terms. Alpha is a constant, it's a number. X is in this expression, so that's the one that's varying. This is the sine wave, effectively. And this is the cosine wave, so that's the varying part of the function. These are constants, and we can now give values to these constants. So for our particular case, we know that cos alpha, just to make sure I got it right, cos alpha is the term in front of the sine, which is 8. So we know that cos alpha equals 8. And we know that the sine of alpha equals 3 from our expression. But of course that's equal to, and there's this r in front of it as well that we're going to need to take into account here. So I can rewrite this as r sine 2x plus alpha can be written as r bracket cos alpha is 8, so it's 8 sine 2x plus 3 cos 2x. putting the r back inside the bracket for a minute, 8r sine 2x plus 3r cos 2x. Now we need to think about what's going on here in terms of this right angled triangle. This is alpha. And we know that the cos of alpha is adjacent over hypotenuse, which is 8 over r. 8 over r. And we know that the sine of alpha is the opposite, 3 over r. So we know that's 3 and that's r, because we know that the sine of alpha is 3 and the cos of alpha is 8. And r will be the length of this hypotenuse. So now we can work out what r and alpha are. Because r is given by Pythagoras, the square root of 3 squared plus 8 squared, and alpha is the inverse tan of the opposite over the adjacent. And so we end up with two formulae that if you need to use them, you'll be given in the exam, which is that r equals the square root of 3 squared plus 8 squared, and alpha is tan to the minus 1 of opposite, which in this case is 3 over 8. So I can work out what r and alpha are, which means I can rewrite our particular solution in a more convenient form. What is the square root of 8 squared plus 3 squared? So we work out that r is 8.54 and alpha is 20.6 degrees or 0.36 radians, however you want it, often in radians. And so now we can put them into our particular solution and end up that y equals, now if we look back at our particular solution, we had e to the minus 3x. So e to the minus 3x times r. So it will be 8.54 e to the minus 3x. And then inside, don't need the bracket anymore, times the sine of 2x plus 0.36 or 20.6 degrees. And that would be a more familiar form for the particular solution, because we now have an amplitude 8.54 e to the minus 3x. That would be our amplitude, and a particular angular velocity 2 and a phase angle. So this would be 0.36. Sorry, this 0.36 would be the phase. So a much more familiar form to see the solution. And if we plot that, we'll see what the thing looks like. So in conclusion, let's have a look at this. Here's the problem we had, this second order differential equation. And if you remember back to that first lecture we had on second order differential equations, we described a second order differential equation for a mass in with a spring and in some sort of damping liquid, and we came up with a second order differential equation like this, look, where m is the mass, eta was the viscosity of the liquid, and k was the spring constant of the spring. And this is a second order homogeneous, as we said, because it's 0 on the right hand side, ordinary differential equation. And we've looked at an exactly analogous idea. In other words, in this particular one we've got the mass is 1 the viscosity of the liquid is 6 and the spring constant is K. And if we go through what we've just done, just quickly once more, we solve the quadratic equation. And then we end up with a general solution. And then we find a particular solution, which involves differentiation, use of the product rule, and out comes a particular solution. And then we can use trigonometric relationships to help us write it in a more convenient form, like that, in other words. And we end up with a wave function. And do you remember from that first lecture I said that was the solution? And there it is. So it is exactly the same idea we've got there, look. The square root of 73 times e to the minus 3t was the amplitude, and there's our angular velocity was omega, was 2, and then we've got a phase angle. So we've done exactly that same idea, and we've ended up with a wave that describes how these things are going to behave. Hang on though. Let's just think about that one more time, okay? And think about all the maths you've been doing for the last however many years on this. Look at what we've just done. All the stuff we've been doing. Quadratic equations. Complex numbers come into it. Okay? And then we end up with having to differentiate to form, not this time, but often, simultaneous equations. What do we use to solve some of the other second orders we've been using? Partial fractions. All this algebra you've been learning, all this maths, means that we can now, product rule for differentiation, trigonometric relationships, we can use to come up with something which is immensely powerful. I never get over this. The maths that we've just done, all this maths, means that we can now describe something in the real world, a mass spring system, taking into account viscosity of the liquid, the mass and all that. Maths is the language of engineering, and so this is a brilliant example of what I mean by that, really. Okay, I'll stop there now before I start to tear up.